Well, this is Mr. Yeager. We are moving on to, this is part two, rotation. Technically, this is my third part for rotation. We're going to look at what's called rotational inertia, and then bring in basically Newton's second law to illustrate how it works with rotation. So that's our kind of two main points for today. All right. So when we are looking at the objects that we want to rotate, we're not going to simply just look at the mass of the object, because it turns out, you can probably figure out that depending on where you hold an object or where you're trying to rotate the object, it's more difficult to rotate around certain axes versus others. And so what we look at is what we call rotational inertia. And again, this brings us back. It's the same inertia as we've talked about before. It's the ability to resist any change in motion that goes on with it. Okay? So rotational inertia is obviously any resistance to a change in rotational motion. Okay? So that's what we're referring to there. So it's not just simply the object's original inertia. The object has some sort of inertia based on its mass and based on, obviously, if it's already moving, its velocity. But again, mainly we look at mass. But with rotational inertia, we're looking at how difficult it is to actually rotate that particular object. Not simply just move it, but rotate it. All right? And again, just to make it clear, this is not, like, the definition always seems to like kind of illustrate a change in motion. Again, this is also the resistance to stop it, which is a change in motion. So this would also refer to the object's already rotating. How difficult is it to make it stop rotating? Okay? So an old name for rotational inertia is called the moment of inertia. This is still used in some textbooks, but in AP Physics, we refer to it as rotational inertia. That's how it comes up on the text. But if you ever see this term on a worksheet or something else, if you're trying to study additional stuff with it, it's always been called moment of inertia as well. Okay? And so what we're looking at is the symbol for it will be I. So it does show up in quite a few formulas we're about to do. It's going to be analogous to mass, but again, you're going to see it's not mass. Mass is actually involved in calculating it, so that's why it's not completely analogous. But you'll see how it replaces some of those things. That's what I have right here. So again, it's slightly analogous. You will see this in how it's placed in the formulas. If you look at our translational formulas and then look at the rotational formulas, wherever mass was, we're going to all of a sudden see this I, this rotational inertia, show up. But again, it's not mass exactly. I mean, really the only good analogs would be velocity, acceleration, displacement, momentum, and energy when we get to it, kinetic energy. Those are very analogous in terms of what they basically are doing. But again, inertia is pretty close to basically referring to the object's mass. Okay? So the thing is, how do we calculate it? This is obviously one of the difficult parts. All right, how do we calculate rotational inertia? It all depends. There's lots of ways to calculate rotational inertia. All right, most of the time it will be given to you in the problem of how to calculate it. But let's go through some basic ways you should know anyway. Okay, for a single particle. So basically, if I have something like at the end of a string, and I'm looking at that object at the end of a string, like say I'm swinging around a yo-yo, and the plastic yo-yo at the end. All right. Anything that's moving around in a circle, okay, that object's rotational inertia on that, on that platform. Same thing would be like a person on a merry-go-round. Each person is a single particle. The inertia of that single particle is always mr squared. It's mr squared. Inertia will equal the mass times where the person is squared from the center, from the axis of rotation. All right. So you can already see what inertia depends on. Inertia depends on mass and where that object is placed on the merry-go-round, placed on the platform that's moving, placed on wherever, where you're obviously rotating that object in the end. Okay? For an object with some sort of a structure, a sphere, a ball, a disc, a rod, these are common ones that will come up. Okay? A formula for rotational inertia will be given. You do not have to memorize formulas for rotational inertia. You should hopefully get used to some of them. There will be some that you'll be like, okay, I've used this one a couple times now. But they're not something you don't have to memorize it. They don't give it to you on your formula sheet. It's given to you in the problem. It'll say, you have a rod, rotational inertia is 1/3 mr squared. Okay, and you don't have to sit there and go, where's that from? That you just accept it. Okay, that's where it's going to be given to you. All right. When we do a system, all right, where you have multiple objects being rotated together, all right, you're going to have to add up all of those rotational inertia. So again, like I said with the merry-go-round itself, the platform that everything is on, is going to be considered a disk. All right. So like I'll draw it out. So we have the merry-go-round platform itself having to be rotated by something. We're going to say it's being rotated obviously right in the middle. Okay. But then you might have people on it. You have different people on it. Each person will have a rotational inertia. So we have a rotational inertia for the whole disk, and then we have the rotational inertia of the individual people. Sorry, just a second. Sorry about that. Here we go again. So what we'd have to do with this particular merry-go-round problem is basically we'd have to find the inertia for the disk, which that would be given to you. You know, in the problem, I think a disk, we'll see it in a second, is 1/2 mr squared. That's the rotational inertia for a disk. And then I'd have to add every single one of these point masses. Okay, that's another name for these. These single particles, you'll refer to them often as point masses. All right, and all of these will be mr squared, mr squared, mr squared. We have to obviously get each person's mass, and then measure where they are on the merry-go-round. How far are they from the center? Okay, is what we would basically look at there. And that would be the system rotational inertia that we might have to then calculate from that point forward. Oops. Skip the page. So here's examples. I mean, again, you can write them down. You can but they will be given to you. You can see a thin hoop. This would basically be the hula hoop example. All right. Its formula would be mr squared. So it actually had the thin hoop is exactly the same as a point mass, even though it is a structure. But the fact is, it's completely hollow in the middle. There's nothing in the middle of it. It's the idea that it's just a round hula hoop shape, okay, with zero mass in the center of it. A sphere has a formula of 2/5 mr squared. All right. Again, none of these are worth remembering. Disk, again, I swear it's 1/2 mr squared. You know, we do get some interesting ones down here when we're looking at rods, or like these, like basically planks, bridges, things like that. The rotational inertia for these objects will depend on where you are rotating it. And so you got to pay attention here. There's a couple of unique things obviously on these formulas where, one, you can see it's not R, it's L. So L means the full length of the plank. The sphere, obviously we'd be looking at the radius from where it's being rotated from the center of it. But for a plank or a long rod, a stick, you know, whatever you want to say, I usually use a meter stick in class and obviously illustrate it with a meter stick. That we'd have to look at the whole length that I'm trying to rotate in there. But then I need to know, am I rotating it from the center of the rod, or am I rotating it from the end of the rod? And those are the only two spots we would look at. But I mean, again, in class, what I do is obviously, like, I have the meter stick, and I mean, just consider. I mean, if you have any long object, if you have some sort of long stick, plank or whatever, think about it. If you have a lacrosse stick, a bat, or anything, hold it like in the middle, try to rotate it, and then hold it at the end, and obviously you'll try to rotate it. You can see that 1/12, the inertia while you rotate it through the center is always going to be smaller. It's easier to rotate it when you hold the object in the center than at the end, because then you're swinging the entire weight back and forth, while in the center you're only kind of carrying half the weights on either side. Okay? So that's, again, some of the questions you might get is just, we'll see in a second, is what's more difficult to rotate? Okay, what's difficult to rotate? All right. So again, you don't need to memorize any of the formulas as seen on the previous page. I would recommend trying to remember this whole mr squared idea, all right? Because there are some things where I feel like that seems to be something that should be implied, or, I mean, I want to say they will always give it to you, but if they don't, this would be the only one that they try to, like, challenge you on to try to remember. It's just that the inertia of any object is related to mr squared. Obviously, there might be some fraction involved with it if you get a structure, but mr squared. And again, things to think about. Obviously, what we're saying is the larger the object, the more mass, the more inertia. Okay? But also, the farther away the object is from the center, the more inertia. Okay? It's easier to push somebody around one of those little playground rides, the little ones that swing around and around and around in a circle. It's easier to push them when they're in the center of it, but if they're on the outside, it takes a little bit more force or torque, as we're going to see in just a minute. Okay? So that's something just to be aware of, and obviously there's a squared relationship there. If I double the distance, the inertia actually quadruples. Ugh, I think this thing keeps on skipping. So here's an example of basically just what's more difficult to rotate. So we have these three rods. I'm not going to read through the problem. Basically, you have a mass. The little square is the mass at the end of it, and then you're just showing you like where are you gripping the object. So what would be, you have to think, what am I trying to rotate? How difficult would it be to rotate that, et cetera, et cetera. Okay. So you can see one. They're rotating it, they're gripping it, the mass itself. So how far is that point mass away from where I'm rotating it? The answer would be 0. Okay? I'm gripping it down here. So this is the point that I'm rotating it back and forth. So the mass itself, even though the inertia for this would be mr squared, if I talk about the point mass, the radius is 0, so there is no inertia coming from that because it's right on the axis of rotation. Whenever you're on the axis of rotation, there's 0 inertia occurring there because that's exactly where it wants to rotate. Okay? So right here, I'm only rotating the rod, okay, from the end. Here, once again, I'm only rotating the rod, but from the middle. And then over here, now I'm rotating both the rod plus the mass, and I'm doing it from the end. Doing it from the very, very end. So, I mean, just thinking about that, think about how this would feel to rotate each of these. We can figure out which one's more difficult to rotate versus the other one. The thing is, the problem would normally give you all of the formulas. They go, okay, rotational inertia of the rod at the end is 1/3. Rotational rod in the center is 1/12. So it's easier. 1/12 is less than 1/3, duh. So this is easier to rotate through the center. Okay. And then obviously the point mass is mr squared. So if we think about going back to that, the easiest one to rotate would be the one through the center. I think that was B is the easiest. I forget which way it said that we had to rank these. It probably was from most difficult to least difficult. B would be the easiest to rotate. I'll go on back. It would be the easiest to rotate. Okay. And then, yeah, sorry, just blanking out here for a second. This one's going to be the easiest. We know this one's going to be the most difficult because I'm rotating both the rod and the mass. And then obviously A is right in the middle. So it says, person grips these, let's see, I don't even think I have an answer there. So it doesn't even say which way we're going to rank this. So this is either going to be C is more difficult than A, which is more difficult than B, or B is less difficult than A, is less difficult than C. I think it's going to be C, A, B is the way I want it set up. Yep, C, A, B. So most difficult to least difficult rotations. All right, so that's inertia. So how are we going to use that sum? We're going to bring it into Newton's second law with rotation. Okay, so we already know Newton's second law is net force equals m times a. All we're going to do now is with this formula, we're going to replace each of these terms, net force, mass, and acceleration, with a rotational analog, or at least something that's closest to it. All right. So what we're thinking here is force causes a mass to accelerate linearly, translationally. What will cause rotation? Okay. What are the analogs for mass and acceleration? Well, what am I rotating? I'm going to rotate an inertia, and I'm going to use rotational acceleration. So I got I alpha. What causes something to rotate? Okay. So here's your first two. Okay. But what causes something to rotate? We said a torque. Okay? So therefore, our formula, our kind of Newton's second law of rotation formula, would be net torque equals rotational inertia times the rotational acceleration. All right? And this is, again, where I completely understand. People completely mess up where they go, torque is force. Torque is not force. Understand that this then equals force times distance perpendicular, because that's what torque is. All right? So this is, torque is, again, a difficult one, because you're going to see it. There are, I think, 3 different formulas that have torque in it that you need to go, okay, should I use this one? Should I use this one? Should I use this one? Or should I basically set those different torque formulas equal to each other and then replace it with the symbols that are involved in that formula? So that's where we're going to run into more, because there's another torque formula still, or at least another formula that has torque in it. But this basically is kind of our last main point, is that torque equals I times alpha. Okay? Only torque will cause an acceleration, as we said, a rotational acceleration. All right? And again, in this case, now we're looking at the fact that it's not static. It's not going to be a bridge problem. If there's multiple sources of torque, we have to add / subtract all those. If they're opposed to each other, we subtract them. If they're with each other, we add them up to get a net torque. Okay? So we end with this problem. We have this centrifuge. Hey, look at that. It's already giving you the formula for, or the amount of moment of inertia. We didn't specifically talk about the units. Moments of inertia, rotational inertia is always something mr squared. So this is just kilograms times meters squared. That's your formulas for rotational inertia. All right, so this one's a pretty straightforward problem. You're given the rotational inertia, the moment of inertia, I. It gives you the net torque, man, so this problem's pretty straightforward so far. Okay? And it's acting on the centrifuge, and the centrifuge started at 100 RPMs. How long would it take for the centrifuge to stop? So this is a problem where it's connecting, again, basically dynamics, rotational dynamics, with kinematics. Okay? Because we're looking at how long will it take it to stop, time. So we got to go to a kinematic equation to help us solve for this particular problem. Okay? So if we look at what we have, we are given the inertia, torque, and sorry, I'm being silly here. I think that should be initial. Yeah, it should be initial angular velocity. A little mistake there. It's going to be negative torque because it's stopping. Final, we should have that too. Final angular velocity is 0. I'm going to change it to radians per second. We got to have it in radians, so we're going to have to do a conversion. So what am I going to try to do here? I'm trying to find time. Excuse me. Okay, there we go. So time, what are we looking for? Okay, so we need to get some of the kinematic equations. Okay, but I need alpha first. I can easily find alpha. I have torque, net torque, and I have I. So let's find alpha. Let's get rid of this junk. So this is a pretty straightforward problem initially. Alpha is just going to be negative 0.12 radians per second squared. The object is slowing down, okay, after going in a positive direction. And then I'm left with this formula. So I mean, that's it. I know what the final, I know what the initial angular velocities are, I know what alpha is, but I need the time. The only thing I need to do is I need to convert RPMs to radians per second. How did I do that? We talked about that before. 100 rotations per minute. We have to be in radians per second. I'm going to do the seconds real fast first. Obviously, 1 minute, 60 seconds. And then rotations. One rotation is 2 pi radians always. Okay, that is the conversion I think some people forget. That's where I'm getting the 10.5 at the end. Okay, that's where I'm getting the 10.5. Because basically this is something close to 600 because 6.28, yeah, basically 628 divided by 60. Okay, so that's what we're looking at. So 10.5 radians per second, I can plug it on in, and I solve. Time that'll take for this centrifuge to stop is 87.5 seconds. Okay, so that's again where we make the connection. It's very similar to the old dynamic problems where you solve for acceleration and then plugged it back into a kinematic formula. Be prepared that maybe you have to do the kinematic formula, find acceleration, and then bring it into the torque formula to find the torque, most likely. Okay? That is it. I'm not going to talk about that one. That's the one I'll start on with the next video. All right? Thanks.